So I guess you've seen the description of that talk. What happened is that I joined the Scala Days even on Monday, first talking to people in the compiler team, and then on Tuesday we had a spree, and a lot of things changed because I look at the community and I could interact with people. My name is Denis Rosset. I'm a physicist, so it's pretty far from, like, I would say, what the bulk of people are doing here. And it colors what I do on Spire. Like, I love abstract math, so I'm going to put like a lot of type classes and, play with it. There are many libraries in the Scala ecosystem. People like to build abstraction, and maybe the library is beautiful, but you don't have much documentation. I would be in that camp, but I realized I want this to be useful, so maybe we should extract something nice out of it, and give it to the community and make it accessible. So basically, I get my money from Permeta Institute, which is a public research institution. I'm paid by some foundation that gives money for foundational physics. Like, I don't need to do anything useful, and for love, I work on type-level Spire. You have different ways to contact me. The best is my email address. I'm new to Twitter, but it seems my dark messages are open, so feel free. And I have a GitHub account with like a lot of things, but you will quickly get a feel of, is this like something I can use or share, or it's something I just put there, all GitHub profiles of these things. Maybe before I go with the talk, like just to share how I started with Scala. So I work in quantum physics, and we have something really important in our research called Bell inequalities, just a word. And during my thesis, I realized, I can organize those things, and I want to build a database so that people can look at the research results, and click and display them in various ways. And I realized, which programming language am I going to use for that? I wanted something that was robust, something with static types, something that could run on the web, and something that could interface with Java, because a lot of MATLAB, Mathematica things play well with Java. So then I started to use Scala, and I thought that really nice library called Spire that encoded basically arithmetic and like day-to-day math, and I started to work on it. What I want to say is that I did not write Spire. I'm just like the current maintainer, and I realized what it is to work with a legacy code base. There are parts that I just don't know how they work, and to understand how they work, it would take me a month. So still, I'm going to push this forward. A few things about the title. There are like 3 keywords: number, type, and Spire. What's a number? It's actually a good question. We have integers. In math, we have real number, fraction, complex number, polynomials. But I think maybe in business, you will work with timestamps, GPS coordinates, time offset. Are those numbers, or do you manipulate them? Money is also could be like a number, but there's maybe a currency attached to it. So it's a good question, I think. Like, what's a number? Second thing is type. And here we move to something else. It's really nice to work with abstract math, and I have colleagues who are very happy to prove that something exists, even if they can't show it to me, like just an existence. But when you work on a computer, you need to be able to represent what you're doing. And I think the most important question is, how do you encode numbers on a computer? What's going to be the data type? What are the operations you can do? The API. And often, like, writing an API is going to steer users towards doing the right thing or not. I think a lot of people know like FP, because if you use FP, you're kind of forced to do the right thing. The internal representation that goes with the first one, and you're going to take as well like care of how do you interact with the world. And people who use JSON, for example, how do you transform numbers between JSON and Scala? It's actually not very clear if you want to be precise. I'm not going to speak about that, just to say that it can be an issue. What is Spire? I already spoke that it's a type-level project. I did not start it. Now it's compatible with CAT. So there is an intersection between CAT and Spire. It's basically equality and comparison order. Then on top of CAT, you have Twitter. There's something called algebra that basically makes that Twitter and Spire use the same abstraction for numbers. Twitter has something called algebra that I don't know much. Spire is 8 years old. It's a medium-sized project, 33,000 lines of code. So you see, like, porting that to Scala 3 is going to be fun. And the version number is not 1.0. And that's our big problem. Like, how do we get to 1.0? And I can tell you, like, please use it. Actually, I came to Scala Days, like, oh, I'm going to advertise that library and everybody is using it. And then I realized, who is going to port those like 50,000 lines of code to Scala 3? Should I tell you to use it if we don't have a migration story, It's very different between being an academic and writing code just for this year paper and then you forget about it, or running a business on it. So, I have a cultural gap. So the end of that talk is going to be me asking question, what do you want out of this? So what has Spire inside? There is an API for numbers. If you work with the Scala standard library, you know that you can, for example, on any collection, you can call .sum, and it's going to give you the sum of things. But you're not going to call some double, some float, some int. There is a mechanism that whatever is your number inside your sequence is going to compute the sum of that. Spire is this on steroids. Like it's much more precise and it gives you much more expressibility. Maybe too much, we'll see. That goes with like generic programming. If you use Go, you need to write some operation for every type. If you use Scala and Spire, you just write it once, and then it's available for whatever type as that API available. And finally, we have data types. If you need to work with fraction, rational numbers, they will give you exact computation on your computer. And we have a bunch of things. Maybe interval arithmetic is going to be useful to represent a number that you don't know very precisely. And like complex and quaternion is more like fancy stuff. That's I wonder how many people actually use it. What I want to say, what Spire gives you more than the standard library. I mentioned that you can take in Scala, you can take any sequence, and this would be like the mechanism on 2.13. On any sequence, you can call sum, whether like your elements are integers or double floating point numbers, it's going to work. Why? Because when you call the method sum, there is an implicit or no delegate for Scala 3 that's going to come into play, and it's going to do the right thing, start with 0, and add those numbers one by one to this accumulated sum. And it works really well. But there are like 3 things that could be done better. The first thing is that it's not very precise. If you say this number is numeric, you have to actually extend ordering, and you can be more precise than that. So as an example, if you work with quaternions, some people do like 3D graphics with quaternions, or complex numbers, for some reason you use complex numbers, maybe in electrical systems. Those numbers, they are on the plane, they don't have an ordering on a line, so you would have to lie there. Like in Python, you define a class and you just do sys.error not implemented, which is not very Scala-like. And there are a few things that I don't know the semantics of, like there is this API and I don't know precisely what it is. The second thing is that every time you do a sec sum, it will box. So if you have an array of, a million double floating point numbers and you call sum on it, maybe the inliner is doing something clever today, but in, let's say, 2.10, it was not doing something clever. What it's going to do is allocate a million double boxes on the heap and, manipulate them and give you returning something that's a box of a double, and then bam, bring it back to a primitive type. So you're going to have like crazy allocation, and if you have like odd spots in your code with that stuff, it's going to be slow. So then maybe you're going to write a while loop and go back to something you would do with Go, which is not maybe what we want. And the last thing is like, when you say something is ordered or something as a plus operation, there are like a series of laws that they should obey for people to build the algorithm on top of it. But those types don't specify exactly what are those laws, and you have no way to check them. So this is what Spire brings to the table. Now I'm going to the plan, and I just want to check the time. That's very nice, 10 minutes. It's going very well. I'm going to dig a bit more into those things, speak about numbers. Maybe you all know about it, maybe not. Feel free to ask questions, interrupt. There is some slack in that presentation, so it's more laid back, not trying to cram. Second thing, I'm going to show you like how Spires provide APIs for numbers. I'm just going to give an overview, and then I have a benchmark where I'm going to see how performant those implementations are across the JVM, JavaScript, and Scala native. I really wanted to do GraalVM, but I don't understand well the performance story there. I didn't want to add something on top, but that's the plan also to look at that. What are numbers? So no, I will add something. I put like natural numbers, and everybody know what they are. But I remember being here, like in Geneva, Switzerland, and in primary school, and we learned what numbers were, and they tried to teach us about binary and decimal bases when we were like 8 years old. So it was very useful for me to go into computing. But normally, we all went to school and we learn about natural numbers, something that we know what they are, like counting. And then, if you have a way to represent natural numbers, you just add a sign and maybe a zero, and you get basically the signed numbers. And that's a type that's very easy to represent on a computer. You just allocate as many bytes you need to encode all the bits that compose your number and the sign for whatever sign representation you use, and bam, you have your type. Very easy. If you want to represent fractions, it's something what's going next when you do like first year mathematics at the university, looking at fractions. It's very easy. You take a signed number for the numerator and a natural number for the denominator. Or would you do that in a programming language? It's just a tuple of big integers. But then something weird happens when you learn about real numbers. So I took the Wikipedia definition that's actually pretty cool. So it's a value of a continuous quantity that's basically a distance on a line. It's very natural, but how would you represent a distance along a line on a computer? It's not very clear. So then maybe you look, how do mathematicians construct real numbers? And it's crazy. So there are like 6 constructions. I don't understand them. But the thing is that none of these constructions can be, you can do that efficiently on a computer. Sometimes even impossible to compute with that. So what do? You resort to approximations. So there are 2 ways to do that. And I realized something like these bangs, and then you have like clicks. I will remove my badge and then we get rid of that. Maybe not. This should be better. Yeah, there we go. Maybe not. I will not move. So what do we have here? As we've seen before, if you compute with rational numbers, it's exact. You will never have precision issues. But you're very limited. You can only do the 4 basic operations. No way to compute the sinus of something, for example. If you just want to use like roots, square root, for example, you can move to something that's called algebraic numbers, and you have those operations on top, and you can still compute exactly. So maybe, I don't know if you do geometry and you want to intersect, I don't know, maybe engineering problems, you want to intersect a sphere with with a surface. Maybe you're going to use algebraic numbers and you're sure that your computations are correct to the end. But I want to say that computing with exact numbers, it's very hard in general. On the slides, I will have a link. You can look that actually it's proven it's impossible to do that, to use like everything you want and be exact. So the other thing that people do, they use approximations. And in the JVM world, we have basically 2 different types of approximations. Either you just write an integer and then you decide how many digits, but decimal digits go on the right of the comma. That would be big decimal. Or you say, I have the same thing, an integer, and I move digits to the right of the decimal of the point, but now it's in binary representation, and that's going to be floating point, and it's the usual float and double. There is a third approach that's used more like in mathematics, like Mathematica, that basically you keep the whole expression in memory, and when you need to do computation, you maybe traverse that tree and ask, maybe 15 digits was not enough, let's do more, and you compute more and more digits until you're satisfied that you have a correct answer. I don't know much about that, and it's not in Spire, so we can move. Now the thing is like, why does this matter? Actually, it's fun because if you compute with a lot of numbers and you do, I don't know, a million or billion additions, in the end, maybe you're going to present a summary of those numbers, like accounting. You're going to present a balance sheet. And if you have like a 1 cent difference between, I don't know, billions, accountants don't love that because they see if you have like a small imprecision, it's probably that something bigger is hidden underneath and they will really dig through your stuff. So if you compute with money, you're not going to use floats because fill an array with 10,000 floats and of like 10 cents, and you sum, and it should give you 1,000, but actually not 1,000. It's something, there is a very small difference. So this is why you use big decimal, because big decimal is on base 10, so something like 0.1 can be actually represented exactly on the computer, and when you do the same thing, you get actually 0, which is what you want. When I see people doing like blockchain stuff, Bitcoin and so on in JavaScript, and they don't use the correct floating point, like the correct number type, I wonder like how long they're going to run without having discrepancies in their accounting. So that's important stuff. What I wanted to say, because floating point numbers, they use this exponent based on 2. Something like 0.25 is 1/4. 4 is the power of 2. So if you do the same thing with 0.25, actually that computation is exact. So it really depends what you do. Are you going to use big decimal or floats? Now, what do you have on the JVM, Scala, Spire? I kind of already said that, but I'm going to restate it. The JVM has a few primitive types, but mostly we're going to use those 4. Int and long, they approximate natural or like signed numbers. What they do is they cut like the range of what you can express. It's still pretty big, but depending what you do, you may want something that's safer and can overflow, because they don't overflow nicely. Float and double, they are encoded in that binary representation, but if you look like at what happens when you write them using like human decimal notation, float gives you 6 to 9 decimal digits. The exponent range is still pretty mighty, and double has a bit more precision, 15, 16 digits, and the exponent range is pretty huge. So this is, in practice, never going to be a problem, but often you're going to be limited there. Maybe I give you already kind of a demo of that, because it's very abstract, and we need something to kind of refresh our minds, and I need to distract you a little bit before we go on with more abstract stuff. So what's this? I don't know who has heard of the Mandelbrot fractal? Because I was fascinated with that as a kid. I was like 7, and I realized I can do that right now that I'm 36. I can use that stuff, to talk about numbers. It's pretty cool. So what happens here is that I refresh that thing as fast as I can. I show the FPS. So that's kind of a benchmark, like how fast can I compute that image. I'm using Scala effects, and I did not optimize the graphics backend, so it's pretty stupid. But I'm not losing. It's not a hotspot. I'm not losing much time just pushing pixel on the screen. So it's basically limited by the how fast I can compute. And what I can do, I push the number 1 to 5, and I can compute. You'll see on the console there with float, so 32 bits, double 64 bits. And I have 2 things we're going to see later. What if we use generics? Do we lose performance? That's going to be a topic later. So I'm going to go to floats. And every time I double click, I zoom on part of that fractal. And we said that float have like 6 to 9 digits. So it means every time I zoom, it's a power of 10. Like I zoom 10 times. So maybe after 6 or 7 clicks, we'll see what happens. So right now it looks really good. I zoom to 3, 4, 5. Okay, it's 6. So now I don't have enough precision to actually represent every value of the pixel composing that image. And when I do the iteration that computes the Mandelbrot set, I'm going to have like precision problems. But now if I switch to double, I get like the correct picture. It's still an approximation, but the approximation at that stage doesn't matter. And if I zoom more and more and more, 3, 4, 5, 6, 7, 10, and now I'm at the limit of double. And with the JVM, I'm going to run in a problem that I don't have any type, that's a primitive type that has performance as double. I can switch to something that's called a double-double. It's a clever hack. But now all my objects, because they are 128 bits, they are going to be allocated on the heap. So it's going to be slightly slower, as you can see. I don't still have something on the screen. It's probably going to take 15 or 20 seconds to compute the new image. I'll see if it's not too slow, because I zoom in a random part here, and then I get my image. So you see that if you use float double, performance will be very good. if you switch to more precise types, it's going to be much slower. The same story would happen with big decimal or rational numbers. You get several order of magnitude slowdowns due to precision, the increased precision and memory allocation. Okay, I was moving to this, but I don't know if you have questions until then, because I don't know if that's too abstract to, like, is it useful, or, you know, like feel free to interrupt. Cool. So we've seen like primitive types. Now I want to say quickly something about reference types. So these things, they can stay in the CPU registers. They're going to be pretty fast. This is going to be allocated on the heap, but you can use an arbitrary amount of memory, which is what provides big integer an arbitrary range. You're never going to overflow. It's safe in that respect. Big decimal has an arbitrary range, and then you need to use like implicits right now to decide on the number of digits.
Big integer is indexed by int. So
yeah.
It overflows when it's like a few gigabytes.
Yes, that's correct. I said arbitrary range, but of course we're limited by the memory of the computer. And at some stage, we are even limited by the number of atoms in the universe to encode that number. So indeed, we are never going to have like the mathematical abstract thing. We are always going to run into limitation. The question is, do they matter? But that's a really good question, like remark. Same thing with arrays, like we're limited by the allocation. What I just said, that they're allocated on a heap, so you lose a bit of speed there. Sometimes the JVM is clever and can see, okay, but actually I can use the stack. I did not do like a deep analysis of that, but sometimes it helps. No, what does Scala on top of that? So Scala has a few helper methods on the Java primitive types. When you use them in a generic context, like in collection, they box, so they are going to be allocated on the heap, which is sometimes a performance problem. Big int wraps big integer and brings big integer into the Scala hierarchy. And big decimal, I think it's a wrapper, but I did not dig into internals. It's the same name. Now, if you move to Scala JS, I think Guillaume told me that they did a lot of work to bring the same semantics of the JVM to Scala JS. And they got it pretty, it works extremely well. We are going to see later what's the performance profile. And they speak about the semantics over there. We lose really little. And then Scala native is adding on the primitive types just the unsigned integer longs and so on, but that's to interoperate with C code, which has the unsigned integer types. Now what does Spire does? Spire actually brings the same kind of unsigned integer types, but using any val. So it has this weird performance profile that if you use it in non-generic code, it's as good as a primitive type, but as soon as it's generic or you put it in an array or a collection, it's going to box. And Spire gives you a lot of types that, I mean, if you need them, you know where to find them, like rational number, algebraic, and so on. And the quality of those is really good in Spire. So here in my slide, I have a few references on what I just like touched. Or you can be bitten by floating point arithmetic. There is a really great paper that tells you about like sometimes equivalent mathematical expressions are not equivalent when you compute. So sometimes you need to wiggle things around to get what you want. It's a really nice paper. And somebody else complained about like, oh, floating point semantics were constructed for the JVM. If you're really interested into the internals of the JVM and like the trade-off in the design, that's a great resource. If you want to learn, like use the library, the Spire library lives on the type level, but it's a huge thing. If you want to see like how it works, I've extracted like around 2,000 lines of code from that library. So it's something you can read in an afternoon. It's called Mini Spire. It's over there. I don't have the slides online yet. I'm probably going to tweet them later today. Just take a picture of that screen if you need. And I'm going to move to the second topic. Second topic is API and laws. For that, I'm not going to have slide. I'm going to look at the code. And we are going directly in the code of Spire. Okay, how do I arrange my stuff over there? Bang, and I can put my mouse here. Excellent. So here, I have the mini Spire project, and we are going to dig into the core. And we have here extracted like the interesting stuff from Spire. And we have, for example, EC. EC is to test for equality. So anytime you have a method that has a generic type, and that method needs to know to compare things for equality, you're going to provide that an instance of that type class. Just one question. Who is familiar with type classes here? Who use cats? So it's kind of half the room. As an approximation, you can think of a type class as kind of a list of methods that apply to a particular type. It looks pretty much like Java has something called comparator, something like, well, I don't remember the name for Java, but you're going to provide a function to your sorting routine, or the C library sort, as you pass a parameter. It's a function that takes two elements of your type and returns whether they're like, or they compare. So that's exactly the same thing. Or do you compare X and Y of type A, return true if they are equivalent. But EC does something on top of just providing a dictionary of methods. There is this sentence here, EC should form an equivalence relation. Equivalence relation means if X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. So things will form a chain. And now we can move to something more complex. It's going to be order. It's when you can compare things with like less than or greater than. So this is going to be X is less or equal than Y. And now order is really the thing you want if you want to sort a sequence, for example. And any sorting algorithm that you're going to call will work only because order is sound. And order is sound if you have a few laws that are respected. So the thing is, numbers should always compare, like X and Y, you always have a relation that one is greater or equal than the other. The second thing is if you have a chain, if like it goes both ways, X is less equal than Y and the reverse, then they're actually equal. So now it's going to relate comparison with like the equality that we have seen before. And the last thing is if X is less than Y and Y is less than X, then it basically transmits that relation. And you have like the description of everything here. But if you use Spire, we are going to give you that type class, so the order type class, for types in the Scala library. So for example, there is something, what happens for integers, comparison of integers. So everything is over there. Equality, we basically use the standard Java thing, like the standard stuff on int. And this compare method returns either -1, 0, or +1, like the compare to in Java. It's implemented over there. And on the consumer side, so that's how you define your structure. But now, Spire has also sorting algorithm. So that stuff over there is an insertion sort. We also have faster sort, quick sort. There's also a merge sort in that table in Spire. You take an array of type A, you have like starting and a start and an end point. And you're going to say, okay, if I want to move things around and compare things in that array, first of all, I need to deal with array. So that's class tag. We have to deal with that encoding on the JVM. And we need to compare elements. And we are going to compare elements here. Data, it's of type A, and item here as well. But now we use that operator. And something magic is coming here. Spire knows that when you use that operator and you have a type class order in scope, there is an extension method. Martin on the opening keynotes spoke about extension method and delegates. That's basically that mechanism. For that, you just need to import the relevant syntax from Spire, and you can work with the usual operators, greater than, plus, and so on. And the magic will happen. Like Spire is going to use the type class instead of the either for the comparison on integers, long, or call the method. So that enables that generosity in the code. There is another. The last thing. So here, I don't know if it's actually relevant for your use cases. You probably are using libraries that do sorting, binary search in arrays. But once that problem is solved, you don't need to basically write code that does that. At the end of the presentation, I'm going to ask you, like, are you actually writing code that's where you can shift the number type at when you use it. Like, is it something relevant to you? I'm writing generic code, and at the last possible minute, I decide if I use float, double, big decimal. That's what Spire enables, but I don't know how relevant it is to the bigger community. That's coming later. The other thing that's very cool is that anytime you write your own number type, so something I did here, it was for math stuff, I implemented exact number that I call cyclotomic numbers. They are basically fraction, but then you can use like cosine and sines of rational numbers, and it's very useful for group theory in math. Okay, so I wrote these numbers. You can do square roots with them. It's pretty cool. But I need to test that they work well. So I have this continuous integration over there. And I want to test like all the laws that we know in maths should hold for numbers. So I have like those 100 and something tests. But actually what I've wrote in my own code is this. So these 200 tests, they come from that. I'm saying I implemented that number type, cyclotomics. Check that it's a field. Check that it behaves well under conjugation. Check that it's ordered. Check that it behaves well, like the addition and the order, like translation works well. I just write those 5 lines and I get tests for free. So I think this is where the Scala ecosystem is moving a little bit with cats. That anytime you implement something, you try not to write thousands of unit tests. If you have some structures, you can exploit them and do something like that quickly. So I would say this is the second advantage of using the machinery of Spire, that you get that robustness. I don't know if there are any questions. I went super fast. Like, just to say, what I show you there, we use like the whole morning at the Scala Spree to look at how it works. If this is like a burning question, I will answer it right now. Otherwise, on the last slide, the people of the Spree accepted that I put their Twitter handle or email addresses on the slide. They are at the conference, so you can talk to them or email me, email them to dig a bit more like outside that session. But if there is like a question, I'm glad to answer it right now. Otherwise, we just move to the next exciting topics. Let me check my plan. I still have, I'm close. Okay, so we've done that. I'm now going to see what's the precision story. Performance story. So now I'm moving to the nice fractal that we've seen before. And we are going to see what's the project. This is public. So what I did, I put all the computation related to the Mandelbrot fractal in a shared repository. And I have 3 backends, one for JS, one for JVM, and one for native, that basically shows a window and you can drag things around. So I can look at the performance of all these types on these 3 platforms. But first, we're going to look at all these computation are done. So I'm going to shared, bing, 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 bing. So basically what I have a Mandelbrot thread. It's very generic. It takes an abstraction that tells me how to push pixels to an image and like what's the current viewpoint in the fractal, or where did I zoom. And I have 3 implementations of that thing. 2 of them are specialized, like the way you would write code in any programming language. You pick the type you're using, and then you write everything with that. So I'm going to look at float, and then we are going to see that double is basically cut and paste and find and replace. So the main thing is that iteration function. I'm basically taking a position in the plane, and there is like the rule of how do I iterate that number until it escapes. So that's the story of the Mandelbrot stat. I check if it escapes that while loop or not. And if it escapes, then I plot how many iterations did I need to escape that the set, or I just loop and I have a cutoff, like that's the max iterations. So it's really pretty standard arithmetic. But now what I did was to say my coordinates are floats. So if I need to change the number to get a bit more precision, I'm going to do a search and replace and put double, and maybe later put big decimal or something else. So all of this is pretty boring, and you can introduce bugs. So the other way is to use generic code. And as you can look, it looks pretty similar. I just did something for optimization there. If I need to compute twice something, it's better just to add it. So I define a function that's twice, does just a plus a. But the code looks exactly the same, except this is generic now. And instead of not having a type parameter on my class, now I can decide that I'm going to choose that number type when I instantiate that class. So a type A, and the colon thing, field and order, means I need to have that type, this implicit in scope, to be able to run that. Because those implicit are going to give me the multiplication, the comparison operator, and so on. That's the mechanism we have seen before. I'm not going to dig into that, but if you use that annotation called specialized, what happens with Scala is that you can have generic and performant code. When you compile something with float and double, it's going to create just for you a special version that uses primitive times on the Java machine. So what I'm going to do now for the performance story is to run the code that we have seen 4 times. One, the float implementation, once the double implementation, and then the generic implementation that uses Spire and float and double. But I'm basically choosing that when I instantiate the thing. So if I look at the, let's say, Scala FX backend, over there, I basically have my computational engine here. It's in a var, so I can switch it. It starts with the generic double, but when I press one of the digits here, I'm just going to switch it either for an instance of float, double, or the generic that now takes a float parameter or generic that takes a double parameter. And I make the decision of which one to use when I create an instance of that class. So let's see how it goes for the performance of that. So I'm switching to the JVM project, running it. So right now I'm using float when the code is specialized. I specialize by hand. I'm around 4.5 frame per second. If I switch to double, which doubles the precision, you see that basically the speed is exactly the same, because the CPU is using exactly the same path to compute with single precision or double precision. Double uses twice the memory, so if you have big arrays, that may be a decision you're going to make. I want to cut memory use in half. Or if you want things on the GPU, that may be a choice that GPU will be faster for single precision. But if you just run this on JVM, the story is more or less, and you don't use memory, then the story is the same. Now, what's really cool is that if you switch between generic code that's specialized when you call it, or code that you specialize by hand, basically you don't see any difference. So Spire has all this crazy magic to enable you to write generic code. You can write a sum function on any array type, and the performance is going to be the same, whether you specialize by hand or you use the specialization mechanism. I think that's a great achievement of Spire. I don't want to get your expectation too high, because if I now switch to JavaScript, so the same story, same code on the computational side, but the graphic backend is different, of course. And you have the frame per second in the little side over there. I don't think it's very readable for you on that screen, but it's basically 4.5. So what it means if you have numerical code that runs at some speed on the JVM, on the modern JavaScript engine, is going to be super fast. I think that's a great achievement of the Scala JS team. But one thing that actually works less well on Scala JS, if I switch, so that's to specialized code by hand, and I go now to the generic double, I lose. God, I don't think you can read that number well. Like, the colors are very different. Can you see that number here? Okay, so I'm going to tell you what it is. I'm on the specialized path, 4.5 frame per second. I move to generic double, no. I think my in JavaScript JIT kicked in, it's warm now. Actually, there is no difference. No, not so much when it's warm. That's pretty cool. But now if I do the last thing and I go to native, and I run it, so I got a surprise doing that. But maybe I should remove the debug mode. That's maybe the problem. Check. So with the default options, it's giving me half the performance of the JVM, and I see a difference between using the generic path. I reduce the performance. So this is something I need to investigate. Like I just got the Scala native running this week. I don't know what the performance story is going to be for that. But if we see the specialization is not working for native, maybe we need to rethink the way we provide the mechanism. I'm now really close to finishing the talk. So yeah, I wanted to speak about laws. That's going to be like, I did that on the code. I'm going to skip. How much time remains? Like 3 minutes? And we usually finish on time, right? So let's do this. Now I have a few questions for you. First question, who has used generic programming? Do you use sec, sort by, sec, sum, ordering or numeric? Who uses that? Okay. Who has used float and double in their code? Okay. Who has used big int? Okay, cool. Who has used big decimal? Nice. Have you used other types for numbers? And can you just tell me what those number types were? Like just shout. I don't think we need. Rational from Spire?
No, in other languages, but in principle.
Okay. And in Scala, like other types in Scala, is it like the same story or? Okay. So I'm going to change my questions on the screen. Would you like, did you know that rational was available for Scala or things like that? Would that be useful for you? Like, I just want to get a feeling. Maybe it's not that important, you know. And I need to know where we take Spire, like as an ecosystem. Would you know about Spire before coming to the talk? Okay. And are you using it? Who is using it in projects? Who is using it in production? God, that's scary. Okay, we need to talk. We need to talk. That's the most important message. I still have 2 minutes for that. What I want to say is Spire has a very precise core. Like the all algebraic operation and structure, like the type classes, it's beautiful. Maybe it's too precise. We have things like non-commutative, additive, semi-groups. I've never seen, even in abstract math, I've never seen that used. So maybe we need to drop it. But that's basically API design, and I'm not going to be the only person having an input there. We have excellent number types, like algebraic, it's crazy code. I don't understand that code, but I've exercised it for many angles. It never broke. So that's really cool. The rest of the code, the quality varies. We have around like 50% code coverage. CATS is nearly 100%. 50% is, we don't have any excuses because we basically have everything as a type class. Everything can be checked. We should get this at least to 75 or 80%. The other problem is that Spire became kind of the magnet for everything related to numerics. So a lot of people contributed their pet class or pet feature, and now it's very difficult to see like who did that. Can they tell us about like what the design consideration, because we need to port it and we don't know exactly what it does. So that's a problem now. That code quality is over the place. Spire has really clever performance hacks. Use macros all the time. And on Monday, I discussed with people on the compiler team, and they said for .T3 we are considering dropping specialization. And that's basically the whole Spire story. So what do we do with that? They said, look, we have inline, we have staging. So we are going to change the mechanism that Spire uses. But that means maybe that we are not going to port 50,000 lines of code to a complete new mechanism. So we need to decide like what to do. The other problem is that Spire is big. Like the bus factor right now is like 1.5. Lars is helping a lot with like managing general stuff, but I don't think he used the code base and the internals a lot. And I basically don't understand some parts, but understand the rest, and both of us are active. So it's kind of scary to say like you guys are using that in production, and I don't know, what's going to happen with it. So I would say it's okay as project health and community goes. So on Tuesday we had the Scala Spree. We use mini Spire. The previous Scala Spree I used the big Spire. And when I used mini Spire to onboard people, they said, "Oh, it's really nice. I want to contribute. I want to do more things." So I realized, okay, maybe we should have something that's way more accessible for people to contribute. So the idea right now is this, but I just got this idea during the week. So I really need your input and your feedback on that. We want to identify core features, and for each of those features, have a clear migration story. Reboot the project. So for a long time, there was this Scala Z project with a lot of symbolic operators and a community culture that was maybe not beginner friendly. And CATS started like having good documentation, trying to onboard beginners. And I think we can do the same for Spire, like reboot the project and provide a better contributor experience. And I would say we only add features to that reboot when there is community traction. Not because it's nice to have some abstract mathematical type, but because people will be using it and hopefully in production. The last thing I want to say is that people on the Scala spree said they are okay to share their communication details. So I put like the name of people who look like a whole day at Spire internals. So they will be able to look at the code with you and tell you a few things. And I'm here doing until Friday afternoon to interact with you as well. I think that's the end of my talk. That's the end of my time. I'd like to thank you, but we should still get some time for like your feedback and your question. You can go and like the talk is finished, but I'd really like that people who are interested in that story to stay and like tell me what you like about it or where you want to see this going. So thank you. So mics and so on, I don't know how it works.
Oh, yes. Do you have finite fields in Spire?
I think we have, like, it's at least in the tests, like
Okay.
there's a class, but now that we have singleton types in Scala 2.13, we should like put we have a much better story for finite fields, and that's a possibility.
And another thing that interests me, you have like complex types like polynomials, intervals, and complex numbers, for example. And in principle, you can compose a complex number of two rational numbers or two big decimals or two floats or whatever.
Yeah.
Do you do that?
Yes, absolutely. And moreover, if you do complex number of integers, it's something called Gaussian integers. You don't get the division, but if you do complex number of floats, you get the division. So Spire has those derivation mechanism that it gives you as much structure as your Scala type gives.
First of all, I want to say that the visualization of performance and precision was perfect. I haven't seen such a good visualization of those things. Another question, maybe more you ask, what could we do with Spire different? So I think there is core mathematics in it, and some, like I'm using in production interval trie.
Okay.
And it's more because of those ranges and so stuff that are more business, they're more of business appealing than some core mathematics. So I think a good separation of those things, what is really, really core and what could be leveraged more in a business aspect. So
Okay. Okay. I love that we stay in touch. Like everybody was a business case for computing with numbers. I'd love to hear your story and have that as like a basis for the next API. So please like send me an email or direct message on Twitter. Like now, and then I'll collect those names and we'll see or we build a community of like, kind of a focus group for what we do next. Thanks for your inputs.
Yeah, let's take one last one.
It's okay. I have two questions, really quick. First, I mean, you focus on the performance quite a lot, and I noticed that you like using the syntax. Does it affect performance because of the extra allocations? Because you need like kind of to create an ops class and then like in the performance.
Okay, good remark. So normally when you have those enrichment methods, you can have an eval or things like that. And then you're going to call a type class, a method of that type class. So there are a few levels of indirection. Spire uses macro to remove extra layers, but you're still going to have an indirection that instead of, for example, comparing floats directly, you call a method that compares floats. What we've seen on the performance visualization is that the JVM is clever enough to inline that, but maybe the native background doesn't know at runtime like where this comes from and is not able to do that inlining. So that's the story. And I didn't use GraalVM, but I'd love to see what it does, because maybe it doesn't have enough information at compile time to do this inlining. Maybe we can provide better hints. I have no idea, but that's kind of a space that opens now. Like until recently, we only had the JVM, but now we have like other platforms. But on the JVM, we do the right thing. Like right now, we do the right thing.
Okay. Do you have for another one?
Yeah.
Okay.
We have to prepare.
Later, like
I
yeah. Other questions? Yeah. Or we need to. Okay.